Hello, Gabby and Christian here with Rebel Outposts at SetonLa Salle, our outreach for robotic and human space explorers as we experiment with extraterrestrial environments. We're here today with Dr. Chuck Wood from, well, where do we begin?
Dr. Wood was a part of NASA's Cassini high-end mission where he reportedly explored Saturn's moon, Titan.
He is a planetary geologist deeply interested in our planet's moon.
He published the Kikuyu Lunar Atlas in 2011, chronicling the gorgeous oblique photographs from the moon taken by the Japanese Kikuyu spacecraft.
Dr. Wood is the director of the Center for Educational Technologies at Wheeling Jesuit University. We just wanted to thank you so much for taking the time to do this interview with us and to ask you a few questions about your background, experience working on the Cassini mission, and the future for space technology. So first off, what made you interested in planetary science?
I saw an eclipse of the moon when I was in the 5th grade, a long time ago. And that was in the 50s when the United States was getting ready to go into space for the first time. There was a lot of news on television. Television had been invented then, it was around. And so we would see in the news pictures of American rockets that would launch and then they would fall down, they would collapse. So it was a time when America was trying to perfect the ability to launch spacecraft. And seeing an eclipse of the moon just made me think, wow, that's a place. That's a place that has different locations on it. It's not, if you look at a star, even in the most powerful telescope, a star is just a point of light. But if you look at the moon, you see it's thousands and thousands of different features that could interest you about what they are, how they perform, and are we ever going to go there? So I think just the environment I grew up in with the moon race and seeing the eclipse, and I read a lot of science fiction, all those things influenced me into becoming an astronomer, in particular planetary scientist.
All right. Our next question for you is, why is the research of Saturn's moons important?
Sometimes when I ride on an airplane somewhere, you talk to the person next to you, oh, what do you do? And most people have normal jobs. They work for some company selling something, fabricating something, whatnot. And I've always felt a little bit awkward in those conversations when I say, well, I study Saturn's moon, a Titan that's billions of miles away. And oh, by the way, it cost $3 billion for the Cassini spacecraft to be built and to flown there. So I get a little defensive sometimes about why, just as you said, why is it important for humanity to do this? And one of the fantastic things we found out about Titan is it's really like the Earth. It has an atmosphere. It's the only moon that has a decent atmosphere. And the main constituent of the atmosphere is methane. And it's very, very cold there. It's 90 degrees above absolute zero. We're a couple hundred degrees above absolute zero on Earth. But methane, which is carbon and hydrogen, methane is in 3 different physical states. It can be a solid, it can be frozen, it can be a liquid, it rains on top, and it's a gas in the atmosphere. So that's just like the Earth. On the Earth we have water. There can be ice, glaciers or snow, it can be rain, and it can be oceans. So Titan is like the Earth. And if we want to understand an object in the universe, if we want to understand a human being, it's a lot easier to figure out what's common and what's normal if you have 2 human beings, or 4 human beings, or 100. And the problem with trying to understand what makes Earth unique and how the Earth works is, of all the planets in our solar system and moons in our solar system, there aren't others that look like the Earth. Titan is the closest one. Titan has the same sort of atmosphere, solids and liquids. And so if there are 2 planets, 2 worlds in the solar system that have evolved this way, we can probably learn more from having 2 than 1. So we want to understand the Earth, the planet we live on. We want to understand how it works, how it was formed, what's going to happen to it in the future. And having now 2 places to study instead of just 1 makes it more likely that we derive correct theories.
So can you tell us a little bit about how you got involved with the Cassini mission?
NASA writes announcements, and they send them out to scientists all over the U.S. saying, we're going to do this project, and we want scientists to propose to be part of the team. And so in 1989, how old were you in 1989? Pretty young, right?
Were you born?
In fact, that's right. In 1989, NASA sent out an announcement saying, we're going to send a spacecraft to Saturn, and we want to solicit scientists to be part of the team. So I wrote a proposal, and I learned a year later that I was selected for it, and then 2 years after that, NASA finally got all the money from the federal government to build the spacecraft and to do it. So I've been on this team for 27 years now. It's just amazing. We've had some people on the team die of old age throughout this mission. Other people have just disappeared. We have no idea what's happened. They retire and not tell anybody. So the way you get on a science mission with NASA is you have a background that's relevant. I had studied the planets, written papers about the moon and the planets, and the Cassini spacecraft has a radar that is necessary to see through thick clouds on Titan. If you just use a normal optical camera, you get very fuzzy images and no images of the surface at all because of the thick atmosphere. It's cloudy every day on Titan. And so the radar penetrates those clouds and sees the surface. And I had worked on another NASA mission where we had a radar flying in orbit around the Earth, so we could see through the clouds, so we could penetrate, radar penetrate from the surface a little. So I had relevant expertise that allowed me to make a case, and I fooled NASA, they accepted me.
Our next question for you is, what are the day-to-day tasks from working on the mission that made it last so long?
There's a variety of them that change over the course of 27 years. The early days, 2004, that was when the spacecraft was launched from the Cape in Florida, and it got to Saturn. I don't remember when it got to Saturn. You were alive by the time it got to Saturn. And once we got in orbit, 97 was launched. Yeah, 89 is when I wrote the proposal. That's right, 89. Launched in 97 and got to Saturn in 2004. That's why people died of old age. The mission took so long. Once we got there, we got the first information back. The radar penetrated the clouds, showed us the surface of Saturn, and we were excited. You know, all this time we finally saw something that no human had ever seen before, and we tried to interpret it. What does that tell us about this moon Titan? What it was made of, and what geologic processes are active there? What else is happening? So we would get together whenever there was a flyby of Titan. At the beginning, we would all go out to the Jet Propulsion Lab in California to see the data as it came in. It's exciting. But pretty much since the second or third year, we just stay at our home, wherever our home institution is, and we look online, just like we're using Skype to see each other. We looked online to see the data as it comes in and to talk to each other, each of the scientists talking about what they see, what do you think that means, what can we do with this data. And then we write papers. Cassini has more than 300 scientists from different countries that are involved in the different instruments, studying Saturn and all of its moons and its rings and Titan. And so these 300 scientists have thousands of scientific papers, scientific articles published in journals describing their discoveries. And so I said earlier that this mission cost $3 billion, but in terms of the scientific output from it, it's been a real bargain. We have discovered so many things about how Saturn works, and thereby we can apply them to other planets and to Earth, Moon, to help understand that. So it's really been a very effective mission.
So how did the radar technology evolve throughout the 27 years of the Cassini mission? And were you able to recalibrate or change anything after it launched?
Yeah, exactly. That's one of the wonderful things about it. The answer is yes. You know, when Cassini was built, the spacecraft was built in the late mid-90s and launched in 97, we had to use the technology that existed, the computers that existed at that time to send out to Saturn. And since then, we've gotten a lot smarter. Our hardware is smarter, but we can't send a new computer up to Saturn. But what's also happened is our programmers have learned. And so the spacecraft was originally designed to collect data in certain ways. But since it was built and launched, scientists and engineers have thought about new ways to use that existing data. One of the great examples is that the radar sends a pulse of energy from the spacecraft antenna down to the Saturn surface. It reflects back, and a lot of complex computer processing generates an image from it. But radar has distortions if it spreads out too wide, so we have 5 separate beams side by side, and those beams come together and just slightly overlap. And originally we would be a little upset because the overlap areas were out of alignment a little bit, things were awkward. And one of the engineers figured out the reason they're out of alignment, they're looking from slightly different angles towards the surface, and we're seeing mountains and hills that are sticking up slightly different. You can almost think of them as having different shadows depending on the angle of the illumination. And so these engineers and scientists realized that if we matched these two beams together to eliminate the things that looked like mismatches, the amount that we had to shift them was directly related to how high the hills were and the mountains and how deep things were. So 2 or 3 years after the mission was already in orbit, we discovered how we can get topography, the elevations from that. That wasn't planned. That was not one of the things we knew we were going to be able to do. That was developed on the fly as we were out flying about. So that's a wonderful example. And there have been a number of things like that that have happened with different instruments. The scientists and engineers get smarter how to use them.
So what made Titan such a viable target to land a probe?
Titan is bigger than the planet Mercury. Titan is a large world. You know, our moon is tiny. Our moon is I think in kilometers. It's about 3,500 kilometers, about 2,000 miles across. Titan is something like 8,000 kilometers across, 6,000 miles, whatever it is. You may be looking at the number right there. I'm just trying to remember what it is. And so Titan is as big as a planet, but it's captured in an orbit, a moon's orbit, circling Saturn. So it's not a planet, it's a moon. And it turns out that it also has an atmosphere. The atmosphere was discovered in 1944. A scientist that I had worked for many years later used military technology that was used in World War II, developed in World War II to try to spy where Germans were using camouflage to disguise their weapons. And so infrared sensing that could see through the painted camouflage was developed then. And this astronomer named Kuiper, he used those sensors on telescopes, and he discovered that Titan has an atmosphere because out in the infrared, beyond visible radiation, the different gases have absorptions that make it obvious to see what's going on. So we used military technology that had an atmosphere. Titan's the only moon that has an atmosphere. So that made it special too. And because Titan is so big, it's the largest gravity object in the Saturn neighborhood, except for Saturn. And so if the spacecraft goes around Titan as it orbits, not goes around, but if it passes near Titan as it orbits Saturn, depending on how close you get to Titan, you can change the orbit of the Cassini spacecraft. So instead of burning fuel, which is always expensive and rare and limited, you just go close to Titan and it changes the orbit. So you can go over the polar regions of Saturn, you can go around the equatorial regions, you can go inside the ring. All of that because we have a massive body there whose gravity allows us to change orbit. So Titan was a natural choice to be studied in detail because we'd be there often.
Our next question, if you could fix any aspects of the Cassini mission, what would you change?
Um, it's selfish of me to say it because I'm on the radar instrument, and Cassini has 8 or 9, 10 different instruments. And originally, Cassini was going to have a scan platform, and what that meant is the spacecraft would be flying like this around Titan or around Saturn, and there was a platform on it that could move. So you could point the radar instrument over this way, or you could point it over that way, even though the satellite, Cassini, was going this way. To save money, that scan platform was removed. And that meant that every single sensor, all of those 10 different instruments in Cassini, had to be pointed at the same place at the same time. And the problem with radar is radar has to look sideways. It gets the response back that depends upon how far you're looking. And if you're looking, I said about shadows, radar sends out energy and it creates its own shadows. So if you want to see if something's elevated or depressed or flat, you need to see shadows. So radar looks out to the side, and all the other scientific instruments look straight down. So we couldn't take radar data at the same time we were taking data from other instruments. If we had that scan platform on there, we could. And so to save a couple $100 million, I don't know what it was, it's chicken feed compared to spending $50 billion. We took off the scan platform. That meant that all the instruments couldn't work all the time. So there was constant competition. For this particular flyby of Titan, are we going to use the cameras or the sensors that measure the gases in the atmosphere and their pressure and temperature, or we're going to use radar to see the surface? So there was constant negotiation amongst the teams. And if you happen to have a strong team leader who could, beat up on the other team leaders, you could get more time. We had a pretty good leader, but so did some of the other teams. So if we had a scan platform, it would be much more science.
So what hopes do you have for the upcoming Dragonfly mission, and how much of your research has influenced it?
Yeah. That's a wonderful mission that younger people on the team than me have proposed. So it was members of my team that I'm on the radar instrument team that proposed Dragonfly. And so all the different things we learned about Titan and flying missions like scan platforms and whatnot, they tried to incorporate on Dragonfly. And Dragonfly, as you know, is this wonderful drone that's going to be able to fly around and hover, land, make all sorts of measurements that we could not make with Cassini. So it's a wonderful, daring, very daring. Can we make a drone that will work billions of miles from here with very faint illumination from the sun, radio isotopes for the energy source? It's going to be a super mission. And the reason I said the younger people propose this is by the time it gets approved by NASA and built and flown, I'll be dead. So we need younger scientists like you guys to come along periodically to be the ones who get excited about these missions and what we can learn.
So since the Falcon Heavy rocket launched on February 6th of this year, what do you think this kind of technology will have on the future of planetary exploration?
When I started studying the planets, I was involved in mapping the moon in the 60s. We had very low quality sensors and tiny computers. The Apollo missions to the moon used computers that are just one fraction of the computing power that I have in my iPhone. And we did amazing things. But every time we increase the computing power, that's really almost the most important thing, because we can process more information faster. We get a lot more science return. So, if you're going to send the next spacecraft like Dragonfly to Titan, we'll use the best technology we have almost at that time, and we'll have much greater capabilities than we had when we built Cassini. I said almost at that time. If you use the latest brand new technology that hasn't been tested in space, you don't know, how's my iPhone going to work when it's in zero gravity or when it's high temperature or low temperature? And so you can't use the very latest technology. You have to use technology that's been tested. You don't want to go out to Saturn and have your iPhone die.
So do you believe that, that space tourism is something that we will see in the next few decades?
I hope so. In fact, when I was young, when I was your age, I thought I would live on the moon. We had a real failure of intention when we built Apollo. You know, Kennedy said we will go to the moon by the end of the decade. He said that in 1961. We were on the moon 8 years later, 69. And then, you know, the last person who was on the moon was 74, right? 73. It's been almost 50 years, 40-some years, since we had a human on the moon. 50 years after the first Europeans came to North and South America, there were hundreds of thousands of Europeans living in the New World. 50 years after Apollo, there's nobody on the moon. What we did is we said, all right, we've done that. We're not competing with the Russians anymore. We don't have to do it. Just ignore it. So you could have been born on the moon if we had continued a quick exploration policy. But because of politicians, because of the Vietnam War, because we were only going to the moon because we were competing with the Russians, we just stopped. It'll be seen as one of the disgraces of humanity that we stopped space exploration, I think. So yes, I hope that we will quickly have tourists in space. It's not going to be governments, because governments are too erratic and controlled by politicians. It's going to be private enterprise that does it like Elon Musk.
So what effect do citizen science projects such as the Planet 4 website have on research?
Oh, I think citizen science is really good for a couple of reasons. I've used it, for example, on the moon. I read books about the moon. I've studied the moon all my life. And yet every time we get new spacecraft, we get new data, new information we can exploit. And there's the Lunar Reconnaissance Orbiter can see things on the moon that are just a half meter across, you know, things a little bit wider than my field of view here. We can see those things on the moon now. We can see the footprints of the astronauts walking on when they were on the moon. And so suddenly there's much more detail to be looked at, and there aren't enough scientists paid by NASA to look at it. So I noticed there was a type of volcanic feature on the moon that hadn't been seen before. And so for 11 years, I had a daily website, Lunar Photo of the Day, and I had over 1 million people a year come to it. And so I said, hey, how about you guys help me look for some of these volcanic eruption centers on the moon? And I had 8 or 9 people from 3 or 4 countries, and we spent a couple of months doing it. We discovered 50 of these things. We published a paper about it. And so that was citizen scientists, non-scientists, not paid by a space agency, who were making discoveries of things that were unknown. And so that's a useful thing. Citizen science is great. Those people who participated got a real feeling that they were involved in something important and new, which is true. You know, so often school was boring, right? Everybody in the school was boring when there's a survey. And the reason is typically you're not doing anything important. You're not working on a project that is important to humanity. You're not working on a project where the answer is not known. So doing things like you're doing now, talking to me and doing projects where you might be observing through telescopes, that turns people on. It turned me on when I was a kid. And that's, I think, how we have to transform schools. We have to find ways to say, you got to do something that's important to you, it's important to humanity.
All right, our last question is, what advice do you have for students interested in space technology?
Become Chinese. It turns out that the United States has lost its way in space. As I said, you know, we were last on the moon 45 years ago. China has sent 3 spacecraft to the moon. They have another one that's going this year. They're going to bring back samples of lunar rocks. And their goal is to colonize the moon. The United States has no long-term goal for the moon or any place else. So I would say, see if you can immigrate to China. If you don't want to do that, you need to get educated in some subject you yourself are really fascinated by. It might be atmospheres, might be geology, volcanology, that's what I study on Earth and on other planets. It might be physics, how do you determine the physics of the inside of a moon or planet is? Find something that you are fascinated by and become one of the best people in the world. And by the time you finish a doctorate degree in some science subject, you know more about that than PhDs who are 50 or 60 years old. So as you go through school, and typically in high school, you learn things that you've known since Isaac 300 or 400 years ago. When you go to college, you learn things that have been known for 100 years. When you go to graduate school, you learn things that nobody knows. So you have to decide that this is something you must spend your life on. So a lot of people go into medicine, a lot of people go into business because they know they can make a lot of money. If you're not interested in economics, if you're not interested in medicine, you shouldn't go in those fields. There are more important things to do with your life than make. You need to do what's the most neat thing you can find to do. And you probably won't know it right away. But what you need to do now in high school and as you go into college is take a variety of different classes so you prepare. You can't say, oh, I can never be an astronomer because I never took calculus. Until you figure out what you're doing, take a lot of different classes and get a lot of different experiences.
Thank you.
Thank you.
Great. Well, thank you so much again.
Dr. Chuck, thank you. That was brilliant. Some of those quotes I want to put up in other places. So you have an amazing mind.
Questions.
I have one other student who has just one question for you. But before I put him on, I had a quick video question for you. You've been bringing up a lot of as you talked about Titan, there are so many NASA photos that are out there. Are we allowed to use them and intersperse them with what you're saying? Those are public domain.
All the national videos are public domain.
That's what I thought. So we'll illustrate the final rendition of the video. But I want to introduce to you, Peter Kuchke is the commander of our drone club. And so I think he just had one quick question for you. He's been hanging out waiting to ask.
Do you think drones have a future in space?
Well, one of the last questions that Gabriel asked, I think, was about Dragonfly. Dragonfly is a drone that's been proposed to fly in the atmosphere of Saturn's moon Titan. So there's a really daring, looking forward, innovative proposal, which NASA has selected for further study. We don't know if we'll actually end up flying to Saturn. But drones are wonderful. We already do something a little bit like that. We have CubeSats. Have you heard of them?
What?
Cube, C-U-B-E, sats.
No,
They're about this size. And typically to launch anything into orbit,
I'll teach you that.
to launch anything in orbit costs hundreds of thousands of dollars, maybe millions of dollars. But NASA has a program where anybody can build a little satellite that's about 4 or 5 inches on a side, a little cube, and NASA will launch it in space either for free or for something that's just so cheap that your school could afford it. So schools are building satellites that are like drones, they're miniaturized, like drones, they're cheap, and like drones, each one can be separate and have its own capabilities. So yeah, I think drones are going to be used for more than shooting down terrorists in Afghanistan. I hope so.
Thank you.
Thank you.
And thank you. We'll be sending you the video when it gets done. It'll probably take us 3 to 4 weeks to render. You were spectacular. We really appreciate it. I think the kids were a little nervous, so they didn't catch your humor sometimes, but I did. So, and we'll respond appropriately in editing. So thank you. I'll be in touch with other projects. So I really appreciate all your time and you getting here with us. So, and Mr. Schnorr, anything you want to add?
Nothing to really add, but just thank you very much. That was fantastic. I personally really enjoyed it. I was off here on the side, and I learned a lot. So that's always something that I enjoy.
my thought is, as I said, school is often boring. No offense to you or any other teachers.
No, I understand.
So anything we can do to turn kids on, I think is what we need to do.
Right.
I was in the Peace Corps and teaching in Africa a long time ago, and I noticed in a chemistry class my students weren't paying attention. So I climbed on top of the laboratory table, and I gave the rest of the lecture from there. And I had their full attention, wondering what this crazy guy was doing.
Right.
And talked about chemistry. So you do whatever you have to do to try to get through.
Yeah, that's exactly right, yeah.
Well, and hopefully, some year, SetonLa Salle might be able to participate in the Challenger program at Wheeling Jesuit.
Yeah, yeah.
So it is phenomenal.